Definition of the OS. The term OS covers many rules because of the myriad design of the and uses of the OSs. So present toasters through ships, spacecraft, game machines, TVs, and industrial control systems. Born when fixed-use computers for military became more general purpose and needed resource management and control programs. Again, imagine this spacecraft, how complex the different sensors, devices being attached to spacecraft, how it is being controlled and managed by the operating system. So no universally accepted definition for OS. So that's why some resources will say it's better to ask the question why, what OS does, rather than asking what OS is. So it's because OS varies with different computer systems. By just simply saying simply defining what OS is, you can't you can't define in general an OS. But if you say what OS does with respect to the computer system, it's much more appropriate. So everything a vendor ships with when you order an OS is a good approximation that varies widely. So for example, now OS nowadays, for together with the installation or the sysgen of the OS, some application programs are already within it. So for example, MS Paint. But MS Paint is for very basic image editing. Or so for example, word processing. You have WordPad. So WordPad, if you use WordPad, it has very limited feature. That's why you will check if you will install either OpenOffice or Microsoft Office if you want. It's because during the earlier stage of the operating system, there was a lawsuit where the application developers won, keeping the OS creators or the OS corporations, or how you say OS companies, OS companies to limit what is within the OS. So example, if you buy an OS with Microsoft MS Paint++ with the same functionality of that with Photoshop or Adobe Photoshop, you don't need to install Photoshop. For example, you have MS WordPad++, for example, where it also has the functionality, the features of a Microsoft Word. So the problem with that is that they, as OS distributor, you monopolize the application program. So that's why it's a matter of business. Application developers said that they don't earn anymore if the OS keep on upgrading what is within their OS generation. So there's a somewhat a joke for that. That's why Internet Explorer is always why are there still users of Internet Explorer, though it's Edge now, for web developers, it's a pain in their head developing applications that need to be supported by Internet Explorer. But again, every time a normal user tried to purchase a computer system, for example, a laptop, and he or she has no idea on how to install things there, what is within the OS and the laptop or the computer is the only available application program for her or him, making within the market share, how you call that, market users of the computer systems, the normal users plays a big portion. That's why, as normal user, the only available browser within the computer system you bought is the Internet Explorer. So there are a lot of Internet Explorer users still. So they upgraded it, they call it now Edge, which has a better performance and support. So again, that's the question. What's with your OS? But though, there are a lot of things within the OS generation or the OS bundled to the OS. For example, your different system applications. What are the different system applications for disk management? Your your uh, creating new directories, all those things that will allow the user to have an ease of use to the computer itself. The definition also is the one program running at all times in the computer is the kernel, the one listening to all the operations that is happening within the computer. So for example, if you press Control F1 or Control Shift Escape, what will happen? So if you close, if your system, if a poorly designed application runs into infinite loop, what will happen? So there's a certain program running, listening to what is happening to every application running or services running or processes running within the system. So it will check, may it be, check for erroneous or possible uh, possible overuse of a certain resource, so things like that. So everything is either a system program or an application program. So when you say system program, it is the program within the operating system. So when you do a right click, for example, the disk management itself, the uh, device management, all those applications running for useful for the OS management. So things that the OS can do, which OS provides a portal, a sort of portal or way that users can perform those operations. Then you have also application program. Application programs are programs not associated with OS. Its main purpose is to provide a convenient resource or hardware usage for the user. So as you can recall the hierarchy or the graphical view of the computer components. Next to user are the application programs or system programs. So TextPad, for example, allow you to do some text editing to a very complex Unity 3D, for example, doing some programming on 3D games and development. Today's OS of general purpose and mobile computing also includes middleware, so a set of software framework that provides additional services to application developers such as the database, the multimedia, the graphics. So especially say for example Android. So Android has this a lot of middlewares allowing the use of those different frameworks to enable your application performs those sophisticated and complex OS tasks. So overview of the computer system structure. So overall, you have the different devices there and your CPU, and you have a memory. So again, if you say computer, it's just a series of read and write to the memory after being processed, either being catered by the CPU and the different devices. One thing to note that the CPU and the devices can run concurrently and competing the memory access. So one or more CPUs device controllers connect through common bus provided. So the problem is you need to have a higher data transfer speed within your memory for the CPU and your I/O devices or different devices are competing for the memory cycle. So the higher your data transfer speed, data transfer rate of your memory, the better. But again, some other factors may affect. So for example, the speed of the data transfer also of the different devices, and as much as the speed of your processor. So the operations, we have I/O devices and the CPU can run concurrently. So that's the main thing to note, because the idea of a good multi-program architecture is that you utilize the execution of CPU and I/O. You utilize its concurrent execution. That means you allow applications or processes to be within I/O devices and some applications or processes within the CPU. Each device controller is in charge of the particular device. Every controller has a local buffer. Each device controller type has an OS system device driver. So the device driver is the general definition of it is that it hides the peculiarity of the devices. Say for example, if you have an Asus laptop, then an Epson printer, then you have a Lenovo laptop, and it's still the same printer. The purpose of the driver is that instead of manually identifying what specific OS and device you have, it is the task of the device driver to bridge or to connect those external peripherals or drivers to the main system, specifically with the OS. So CPU moves data from to main memory or to from local buffers. So local buffers are those within the device controllers. So I/O is from device to local buffer of controller. So again, this is somewhere in these controllers where the local buffers resides. So again, the I/O device main purpose is the function is from the device to the local buffer. So that means I'm processing something, then I will put the result of the process somewhere in the local buffer. So take note of the CPU's task, main memory to and from local buffer. So that means it's the task of the CPU to check local buffers of the different devices and put it in the memory. Device controller informs CPU that it has finished its operation by causing an interrupt. So in an interrupt-driven architecture, you have every time an IO start, then the IO device is performing the IO request, then after completion, a certain signal is being sent. That is an interrupt to the CPU so that the CPU will try to move that from local buffer or from the main memory to local buffers. So whatever the request, IO request. The common function of interrupts is interrupt transfer controls to the interrupt service routine, generally through the interrupt vector, which contains addresses of all the service routine. So if you're familiar with the assembly language of your graduate study or undergraduate program, the idea with assembly is you program it specifying the certain routine, the certain interrupt routine you need, and specifying the registers you supply or the parameters to the specific interrupt. So that means, for example, you set for a basic assembly code, set the AH or the accumulator AH202, then issue interrupt 21. So what does it mean? So you're calling a certain interrupt, then you perform that interrupt. So whatever the parameter they're using, basically that's requires a data from AL maybe. So causing an echo of that certain parameter within the register being provided to be executed within the interrupt routine. So the interrupt timeline is somewhere where the CPU is busy is the user program. So it's not busy, it's catering something. The IO devices timeline at the idle lane. So once the IO device, upon a certain request, finish its execution, that's this lane, it will issue an interrupt. So you can see there are some latencies there, a certain processing delay time, because every time you interrupt the CPU must load save the contents of its registers to a specific process control block, so that upon resumption of that process, the same or a proper resumption of the process will happen. That means the different contents of the registers are the same content prior to interruption. So that's why there's a somewhat lag or latency here. So upon IO completion, it issues interrupt, the OS saves something, and process your IO request and return back to user program, whatever the CPU is doing at this point. As you notice, at some point here, another IO request was sent. So the IO device must prepare its resources also, maybe the local buffers or the queuing of the request before it will be catered. Upon completion, it will send signal to the CPU and interrupt. Your CPU will interrupt whatever he is doing and process the interrupt or the signal of the IO device. So the OS preserves the state of the CPU by storing registers. So again, we know what are different components of the CPU, the ALU, the arithmetic logic unit. So there, the OS will try to save those information to the sign process. That's process control block, which contains the program counter, the different registers, the files associated with that process, the file management, the CPU scheduling management, and so on. A lot of things about the process. So the OS must preserve the state. That's why there's an idle or the latency somewhere upon request of the IO device. Determines which type of interrupt has occurred. So in assembly, whatever you allocate at AH, move AH06, 07, AH10, A0A. So those things you determines what type of interrupt you're doing. So upon calling in 21 in 10, for example, that is execute the proper routine of that specific type of interrupt. So separate segments of code determine what action should be taken of each type of interrupt. So again, there are ways to execute. That's the routine, interrupt routine, stored somewhere in the interrupt vector. Once it is called, whatever the data being stored to the different registers will be processed and be stored back to a specific register. So most likely at the accumulator and the or you specify different location. Excuse me. So interrupt driven IO cycle. So first the CPU is busy at the user program. Then an IO initiates. The CPU executing checks for interrupts between instructions, meaning it is doing something but checking for the interrupt being sent. So if the request is completed, the IO sends interrupt. So CPU receiving the interrupt transfers the control to interrupt handler. Whatever the data being sent to the register will be processed by that interrupt vector routine. Then the CPU resumes processing of the interrupted task. In this example, it's more of a first method of the handling of I/O. The I/O starts, control returns to the user program only upon I/O completion. So there is also a type where the I/O starts, control returns to the user program without waiting for I/O completion. So, for example, if you perform an I/O request, wait instruction idles the CPU until the next interrupt. That means the CPU will wait. At most, one I/O request is outstanding at a time, no simultaneous I/O processing. So, when are this type of or this method is being used? So if you have an I/O critical operation, maybe there's some process that is doing some out of memory something or unresponsive application. So the CPU must run some service program or service routine to cater to that specific error. So that means while catering to the specific error, you might want the CPU and the OS to be busy on performing whatever the problem is happening. So you don't interrupt. So there are other applications, better applications of this I/O structure, which allows the CPU to wait, which make the CPU wait until its completion. The other one is the after I/O start, control returns to the user program without waiting for I/O completion. Waiting for I/O completion. That means every time the I/O is completed, a system call is sent to the OS. So system calls is more of I am as an application, you send something on behalf of the OS. So the request to the OS to allow user to wait for I/O completion. So it's application level. So device status table contains the entry for each I/O device, indicating its type, the address, and the state. The OS indexes into I/O device table to determine device status and to modify table entry to include interrupt. So next, storage structure. So first, we have main memory, the only large storage media that the CPU can access directly. So if you're if you can still recall the diagram where the OS, the main memory is the one being shared by the CPU and the I/O different devices, I/O devices, where the CPU and the I/O devices are competing for its how do you call that, the the time in memory at main memory. So it is random access, typically volatile. So when you say volatile, no power is provided, data is erased. So typically random access memory in the form of dynamic random access or DRAM. So again, because your main memory is the only storage media that the CPU can access directly, then as much as possible, your data transfer rate or speed of your main memory must as much as possible as say comparable to your CPU processing. So at the earlier stage of the computers, there's a gap between the main memory's processing speed and the CPU processing speed. So some experts at that time say maybe in the future the gap will narrow because of the advancement of technology. But the advancement of the technology, rather narrowing, is widening the gap, because as the main memory access rate or time increases, the CPU processing exponentially increases. So that means supposedly the main memory, the advancement of technology will cause main memory to catch up with the CPU's processing time. The advancement of technology leads to a wider gap. So that's a problem nowadays. But if you set up your own computer, you need to have a faster or faster data access transfer rate or access time of the main memory for the CPU to process its task faster also, or speed up also its processing. So again, it's volatile. That means if there's no power, the contents of that storage will be erased. That's why there's secondary storage, the extension of the main memory that provides a large non-volatile storage media. So your hard drives, for example. So in the storage hierarchy, the main memory is on the top, followed by the secondary storage, the hard drives, and the optical disk. So it's not specified here. So as you can see, this one is the storage hierarchy. Registers are within the CPU or additional registers within the computers. You have the cache, then you have the main memory. Both, all of this at this level are the volatile storage. It means no power, no data. The non-volatile memories are the hard drives, optical disk, and the magnetic disks. So they are in the storage device hierarchy. They are arranged according to speed, cost, and volatility. So on top has higher cost up to the with lower cost storage media at the bottom. In terms of speed, on top are the way more faster storage devices. Then slower at the bottom. The slowest is the magnetic tapes. In terms of volatility, again, it's arranged in two levels, volatile and non-volatile. In terms of storage capacity, so the upper part has a smaller storage capacity. So tertiary storage are more for designed for backup. Secondary storage are for saving of the applications or the OS itself and other data when power is off. By the time uh, the power is turned on in your computer system, the essential applications together with the OS is transferred to the main memory. So when you say caching, it's the copying of information into faster storage system. For example, the main memory can be viewed as the cache of the secondary storage. So you need to copy the information to a certain faster storage media. So for hard drives, you have the disk surface is logically divided into tracks, which are subdivided into sectors. So tracks and sectors. Then you have the platters, then the cylinder. I will have a separate. I will give you some separate video on this uh, hard drive specific topic. So the basic unit of computer storage is a bit. Then a bit can contain one of the two values 0 and 1. Then it can grow into 8 bits called byte. The 4 bits in each 8 bits is called the nibble. Then the modern computer works. You have the device, you have the direct memory access to have a faster data transfer. Instead of waiting for CPU to cater the request, you allow the device to directly access the memory. But there is a sophisticated or complex architect mechanism that to allow to ensure data integrity. Use of high-speed I/O devices able to transmit information at close to memory speeds. That's DMA. Device controller transfers block of data from buffer storage directly to main memory without CPU intervention. So again, blocks of data transfer directly to main memory. So initially, CPU will transfer data from local buffers to main memory, but to allow CPU to cater a lot of other process, you do perform DMA. Only one interrupt is generated per block rather than one interrupt per byte. So we have bootstrap program, simple code to initialize a system, load the kernel. So again, initially your OS, the kernel is running, is in your secondary storage because your main memory is a volatile storage. So the bootstrap program, whenever by the time you load or you turn on your computer, the bootstrap program will locate the location of your OS, the kernel, load it, and load it to the main memory and execute and start those system daemons or system provided services provided by outside the kernel. Then hardware interrupt by one of the devices. Then software interrupt could be caused by error or a certain system call. Other problems include infinite loop. So certain interrupt. So again, the bootstrap program will load your kernel, your OS, and the different startup programs. And not the different because it will be OS specific. Just the kernel. It will load the kernel or the OS to the system to initialize the computer. That's why a faster secondary storage media means a faster boot. So if you're using SSDs has faster transfer access time. Faster transferring from the secondary storage to the main memory allows you a faster boot. So multi-program or batch system, single users cannot always keep CPU and devices busy. Multi-programming organizes jobs, decode and data, so CPU always has one to execute. So that is one job selected via the job scheduling, selecting from the job queue which process or which app program must be loaded. A subset of total jobs in the system is kept in memory. When job has to wait, that is for an I/O, the OS switches to another job. So that's the multi-programming concept. Multitasking, a logical extension of batch system. The CPU switches jobs so frequently that the user can interact with each job. So response time should be 1 second or less. We have if several jobs ready to run at the same time, you perform CPU scheduling. Then if processes don't fit the memory, you move those processes to some virtual location or faster secondary media to allow processing portion or part of the process of the process of the program. We have also allow virtual memory. Virtual memory allows execution of process not completely in memory.